Welcome back. We've been through some challenging material up to this point, and it's great to see that you're following along and understanding the concepts. Remember, we said in the beginning that it's important for you to comprehend the ideas presented because they are a foundation for the material in future chapters. In this lesson, we'll discuss intercontinental ballistic missiles, or ICBMs. We'll understand how the trajectories for ICBMs differ from spacecraft, how the conic sections can be used to explain the paths they follow through space, and some of the history of the ICBM development. We'll also get into the pros and cons of the Anti-Ballistic Missile Treaty. By the way, this is a photo of a Minuteman ICBM being launched from Vandenberg Air Force Base, California. At the end of the last section, we talked about spacecraft that remain in space and even travel to faraway planetary destinations. Today we'll talk about ballistic missiles, vehicles that go great distances through near-Earth space but do not remain in space. We'll start by defining conic sections and the trajectories ICBMs follow. You may ask, what is a conic section and what does it have to do with things traveling in space? Well, all objects moving under the influence of gravity must follow paths that form conic sections. In fact, we've already talked about several conic sections in our discussions of orbits, so this should be a bit of a review for you. Circles, ellipses, parabolas, and hyperbolas are all conic sections because they are all slices of a cone. In the next slide, we'll take a look at these slices of a cone, or conic sections. But first, it's important to understand that parabolas and hyperbolas are trajectories that are useful only for interplanetary travel, while circular and elliptical orbits are great for near-Earth as well as interplanetary orbits. If you've ever had an ice cream cone, you may already know what we're talking about. Unfortunately, we'll have to drop the ice cream here and focus on the sugar cone. If you look at the center diagram, you'll see one sugar cone stacked on another sugar cone that is upside down. We all know that a circle is round. You can describe the circle as the shape you get by slicing the upper cone parallel to the table. A circle is a set of points all at the same distance from the center point. If you look at the lower cone, you'll see that the ellipse is formed by slicing the cone at an angle. An ellipse is just a squashed or stretched circle. The shape of a ballistic trajectory is an ellipse that intersects Earth's surface at 2 points, launch and impact. A parabola is the set of all points that are equally distant from a point and a line. On the left, you can see how a cone would be sliced to get a parabolic shape. A hyperbola is one of the 4 conic sections that describe a spacecraft's possible path in space. It is also the curve that's formed when 2 circles intersect in points. We discussed hyperbolic trajectories as high-energy trajectories that take us to the planets in our solar system and beyond. This has been a very short and sweet discussion of conic sections. Just remember, for the purposes of this chapter, that ballistic trajectories are elliptical in shape and they intersect Earth. The mission of an ICBM is to launch a payload from one point and impact at another. So the shape of a ballistic trajectory is an ellipse that intersects Earth at 2 points. In this figure, the launch takes place from somewhere in Africa to impact in the Pacific Ocean. Imagine your family lives in a house that shares a very high backyard fence with a neighbor. Every once in a while, your neighbor lobs a bag of trash over the fence into your yard. Would you be upset? What if your neighbor persists and begins lobbing car parts over the fence into your yard? What would you do? Well, you'd probably go have a discussion with your neighbor and work something out. Who knows? Your neighbor could be impressed if you tell him the trajectories that the trash and car parts followed over the fence were elliptical in shape and touched the Earth in 2 places, your neighbor's yard and yours. We've mentioned the word ballistics several times already, so let's take a minute to define the term. Ballistics is the science that deals with the motion, behavior, and effects of projectiles, especially bullets, bombs, rockets, and missiles. In other words, it's the science of designing and hurling projectiles to achieve a desired effect. Ballistic trajectories are the paths followed by non-thrusting objects, such as baseballs or ICBMs, moving under the influence of gravity. To analyze them, we note that most ballistic trajectories for an ICBM are outside Earth's atmosphere, and, just as in our two-body orbit example, we ignore all other forces except gravity. We can see here that Jerry's trying to squirt a dog with a water hose. He has three basic options, which are similar to the options we have with ballistic missile trajectories. You may have done this with a dog, a car, or even a friend. Let's start with the low end. Jerry can squirt the dog by simply pointing the stream of water directly at the dog. The path the water follows is slightly curved, and if the water stream is strong enough, Jerry can hit the dog with this low trajectory. If Jerry wanted the water to go as far as possible, he could point the hose so the stream of water would have about a 45-degree angle between the stream and the ground as shown. This way, he could remain as far from the wet dog as possible and still hit him with the water. This trajectory is the maximum range trajectory. Finally, Jerry could also hit the dog by pointing the hose upward at an angle higher than 45 degrees and still hit the dog with the stream of water on the high trajectory. We recommend that you remember this example, or you could be hosed on the next exam. Whether you're squirting a hose or launching a ballistic missile, the effect of flight path angle or trajectory is the same. The ballistic missile can usually reach its target on one of three trajectories: low, maximum range, or high. Maximum range occurs with a flight path angle near 45 degrees. Let's look at a few more details. A real ballistic trajectory is defined by 6 items. The starting point for the ballistic trajectory is the rocket's position or radius from Earth's center at burnout. After the initial launch, burnout occurs when the engine stops either by burning all its fuel or by shutting off the rocket engine. The rocket's velocity or speed at burnout defines how much energy the rocket has, which is a key factor in determining how far the rocket will travel. The flight path angle at burnout will determine whether the rocket is following a low, maximum range, or high trajectory to its target. The direction of flight, or azimuth angle at burnout, determines where the missile will actually go. The latitude at burnout and the longitude at burnout help determine the starting point for the ballistic trajectory relative to the surface of the Earth. And once again, the shape of a ballistic trajectory is an ellipse that intersects Earth's surface at 2 points: launch and impact. Unlike some spacecraft, it's important to remember that ballistic missiles have a set course that we can't alter after it has burned its fuel. The laws of ballistics govern its course. Intercontinental ballistic missiles are long-range missiles that use a ballistic trajectory involving a long rise or ascent and a long fall or descent. Some parts of the trajectory are below Earth orbit and some are at Earth orbit. An ICBM differs little technically from other ballistic missiles. The intermediate range ballistic missile, the short range ballistic missile, or the newly named theater ballistic missile all vary mostly in terms of maximum range. Of course, ballistic trajectories have been important in warfare since someone threw the first rock at an enemy. Throughout history, weapons development has focused on being able to throw things farther and faster. ICBMs are very serious business because they tend to deliver very destructive payloads, like nuclear or chemical weapons that have one purpose only. You'll remember that in Chapter 2, we studied the development of the first real intermediate-range ballistic missiles, although some of them were not called that at the time. In Germany, under the command of Hitler in 1942, Werner von Braun launched the first real intermediate-range ballistic missile, the V-2 rocket. During the late 1950s, the former Soviet Union and the U.S. began to compete in developing ICBMs. And since then, several other countries have also taken part in ICBM development. Modern ICBMs typically deliver multiple independently targetable re-entry vehicles, or MIRVs, each capable of carrying a nuclear warhead, allowing a single missile to strike a handful of targets. The MIRVs were developed because the size and weight of modern warheads were decreasing, just like civilian and commercial spacecraft were getting smaller and more capable. The MIRVs also provided an easy answer to put more anti-ballistic missile, or ABM systems, into action. Adding more warheads to a single missile typically costs less than building the missiles to shoot down the additional warheads. Low-flying guided cruise missiles can be used instead of ballistic missiles. Let's take a look at some specific ICBMs. The Minuteman I and II were the United States nuclear missiles in service from 1960 until 1997. The Minuteman III, which was the second-generation ICBM deployed by the U.S., entered service in 1978 and is still in use. In 1998, the Air Force's long-range plan was to keep the Minuteman III in service until 2025. If you look at the range of dates from the Minuteman I through III, you can see that they were both practical and reliable, and that's due to two important innovations: solid rocket boosters and integrated circuits. The solid rocket boosters, or SRBs, made the Minuteman faster to launch than other ICBMs using liquid fuels. And the technology that was used by both the military and the civilian world was the first mass-produced system to use a computer built from integrated circuits. The Apollo program's flight computer came from ICBM technology. Here you can see an early trajectory of a Minuteman missile fired from Vandenberg Air Force Base in California, shown on its way to Kwajalein Island in one of the many tests that are performed on these systems. Typically, the boost phase, or the period of time that the rockets are firing, is very short. Once the rocket motor stops, the missile is on its ballistic trajectory. This photo shows the Peacekeeper ICBM, which was first deployed in 1986. The Peacekeeper was developed to replace the Minuteman and to prevent hostile action against the United States. The Peacekeeper has an interesting history of being funded, canceled, modified, and reinstated over several presidential administrations. But ultimately, in 2004, the Peacekeeper was removed from service to meet the unratified Strategic Arms Limitation Talks, or SALT II agreement. Design work on Peacekeeper, originally called MX, began in 1972. Besides improving the missile's technology, designers were keen on making it more survivable and mobile. In 1976, Congress refused to fund a system based on placing missiles in silos at stationary launch sites because it was too vulnerable to enemy attack. In 1979, President Carter approved the missile's development and a system of multiple protective shelters linked by rail to deploy it. Here, you can see one of the multiple protective shelters linked by rail. In the event of a possible threat, the missiles were able to move by rail from one shelter to another, hoping to avoid enemy strikes. In 1981, President Reagan canceled President Carter's missile development proposal and pushed for a dense pack solution, which was rejected by Congress as another silo-based system. Here's a picture of the missile rising up from the silo. In 1972, President Richard Nixon and Soviet Premier Leonid Brezhnev signed the Anti-Ballistic Missile Treaty. The treaty was meant to limit the anti-ballistic missile, or ABM systems, which were used to defend against attack by ICBMs. You can see Brezhnev and Nixon here at the White House after signing the treaty. The ABM Treaty stated that each nation may have only 2 ABM deployment areas, restricted and located at least 1,300 kilometers apart. This was so they couldn't create a nationwide ABM defense or become the basis for developing one. Neither country challenged the ability of the other's missile forces to strike back. The treaty was in force for 30 years, from 1972 through 2002, when the U.S. withdrew from the treaty. Among the arguments for withdrawal from the ABM treaty are that it would allow the U.S. to develop a ballistic missile defense system to protect against rogue nations developing weapons like ballistic missiles. The current world situation, with significant terrorism, presents a challenge to our national security, and therefore the U.S. needs a secure environment to continue to develop their new technology. There were many who criticized our withdrawal from the ABM treaty. Among them was John Rhinelander, a negotiator of the treaty, who predicted it would be a fatal blow to the Nuclear Non-Proliferation Treaty and would lead to a world without effective legal constraints on nuclear growth. Russia and China also withdrew from the treaty, but the U.S. has recently stated that it intends to discuss reducing most nuclear warheads if the other countries agree to do the same. Currently, 8 nations have successfully detonated nuclear weapons. These states are the U.S., Russia, France, the United Kingdom, China, India, Pakistan, and North Korea. And you'll notice that another state, Israel, is undeclared, which means they refuse to confirm or deny having an arsenal of nuclear weapons, although it is strongly suspected that they do. Answer these questions about ICBMs and their trajectories. Remember, if you have any problems, go over the material by yourself or with your classmates. Congratulations! We've successfully concluded another section in the Exploration of Space course. In this lesson, we discussed intercontinental ballistic missiles, or ICBMs. We now understand how the trajectories for ICBMs differ from other spacecraft, how the conic sections explain the paths they follow through space, and some of the history of the ICBM development. We've also gone over some of the pros and cons of the Anti-Ballistic Missile Treaty. We just talked about re-entry vehicles deployed by ballistic missiles. Next, we'll discuss those space missions, like space shuttle missions, that require our spacecraft to re-enter Earth's atmosphere and come home. Many of you may have seen television clips of space shuttles entering the atmosphere or the Apollo capsules re-entering Earth's atmosphere and landing in the ocean. Now we'll try to understand some of the challenges associated with these activities.